everyone. Today we'll be doing 16.1 vector fields and then 16.2 line integrals. The vector fields, each section where we'll just look at some vector fields, or we'll plot vector fields, or we can even take you remember like a function of x and y, we can find the gradient of that function, and we can actually make a vector field for the gradient, because the gradient's a vector, right? We get a gradient of that vector field. But first we'll talk about where is this stuff applied. So these images here, I just want to point out, that's I guess one of the more recent hurricanes to smash into the U.S. This is just Hurricane Matthew back from October 2016. As you can see, it's just these little arrows in there. That's the vector field. And it's just representing like they're the wind velocities. So vector fields can be air velocity, air velocities. It can also be ocean currents. But this is just an example. Those are just some images taken. You can see that eye there where it's red. Just from Matthew, Hurricane Matthew back in October 2016. And you see them going in different directions. You see them spinning around. So that's what we're talking about. 16.1. There's some more right there. The length of the vector definitely is longer when it's stronger. If you're talking about a wind velocity, the vector would be longer. But these vectors would get so long they don't get all crammed in. Does that make sense? So it's a good idea. They color code these, or of course where it's red, they're stronger. They're stronger. But you'll notice in the vector fields we have today, we can look at it where it's actually the length of the vector is longer than it's going to be for a value that we put in there, etc. But we'll also look at one like this where everything is just made like a unit vector. That's what's happening here. We're just taking making them all unit vectors, but using the coloring to indicate the strength. Because we get it, all the vectors would jam into each other. It'd be hard to read. So, do you have that 16.1 to 16.2? That's what I titled it. I just titled it, 16.1 vector fields. And we'll actually start with number 2. I thought that's a better one to start with. Where we just talk about how do you plot points in a vector field. So here's 4 vector fields. The one with the 6 parentheses x plus y. And you see the x and y components. There's an 8x, 8y. I can start with that 8. I can start with that 8x, 8y if you want. Hey, is it? There you go. Somebody take all these two. That's all right. Hey, so everyone, we'll start with this 1 8x, 8y. And I'll put that on the board. It's a vector field. And it's a vector field composed of x and y. And it's equal to 8x, 8y. I'm like, well, how do we get started? So I'll actually hit the light just so we can figure out how can we start plotting vectors in a vector field for what we have here. It's very simple. Just pick a point. And you can pick the point, let's just say for our first example, how about 1, 1? So everyone, at the point 1, 1, and what do you do with these values? Notice I just picked a random point. What do I do with these points?
Plug them in.
Plug it in. What do you get for the vector? 8, 8. So at the point 1, 1, what's the direction of that vector? It'll go 8 in the positive x direction, right? And then it'll go 8 in the positive y direction. So this vector should do something like that. It would have a, you can think of its actual length. It'd be pretty long. It's the magnitude of this, the square root of 8 squared plus 8 squared. True. Let's look at some other places. What's going on at the point -1, -1? What happens with that vector? -8. -8. That's how it would move. Right? This is when I'm writing these vectors. This is direction, the movement of it. So at -1, -1, how would this vector be moving? It will go. Let's see. That's x components. So left 8 and down 8. That's the direction that would look something like that. maybe we can get a sense, we can just plot a couple more real quick. How about here and here? What's going on at like the point -1, 1? And this is really the process when it comes to, hey, I'm going to make a vector field. Well, I can plot a point in each quadrant. How will that move? -80. And how about the point, I'll do that one too, that's what? That'll be 1, -1, how will that move? 8, -8. So how's it moving here? Oh, it's going out like that, right? Left 8, up 8, and here, right 8, down 8. And I'm scaling these, because you know they would be really long. Do you all agree? If you think the actual length of these, the magnitude, square root of that square plus that squared. Sometimes it helps to just pick a point like right on the y-axis or x-axis, because in a second we're going to do a matching exercise. And you go, oh, I'm trying to match. This is exactly the tactic we'll use. We'll pick some points. We can also look for patterns. We'll discuss that, but you just end up picking points to see what's going on, to see which vector field would be represented by the vector field equation that's given to you. So what's going on at like 0, 2? What's going on at that point? Ooh, so we'll be moving what? 0, and then
16.
Super long here, but what does that mean? Which way is that going?
Y-axis.
Straight up. That's what we're saying. Like at this point, we're like, wow, this vector would be really long, but that's the direction it's going. Right? A vertical vector is totally vertical. Going right up that, you know, the J component, right up that y-axis. And everyone, so we are matching. So which one is it? Come down to it. Let me just pull these down. These are scaled. We can still get a sense of which ones are smaller, which ones are bigger. Which vector field is it? A, B, C, or D?
A.
That's A. That's definitely A. So when this is going to be vector field A, I'll pull it down a little bit in terms of the choices. So now, all right, that's vector A. Let's go to this one on the left. Let's match this one. So now we're matching. But this one right here, we realize would be vector field A, true? So that one, 8x, 8y is A. How about this one? So all we're going to do, how do I, sometimes students ask me, where do I start? I don't know where to start. I said, just pick a point. And pick any point you want. It can be anything random, but when I see an x plus y, you know what stands out to me? I think of a point like this. I'm going to erase this. How about a point like -1, 1? Or -2, 2? Or -3, 3? I think those are good points to look at. Because what's going to happen? And when I'm talking about that vector field that has 6 times x plus y, and the y component was the same, right? 6x plus y, 6x plus y. Well, I think these are good points to look at. Because what happened to the vectors?
0.
They're all zeros. So let's look in this image. If we can, like, these points, where are they located? On the xy coordinate plane. -1, 1 is there, -2, 2 is there, -3, 3 is there. Let's look at points along here. And we should see open space. Because we're saying they're zero vectors, right? Alright, which one of these 4? I can shrink it down so we can just match it. And I'll hit the light too. Which one of these is actually doing that? We just see it kind of fades out along that line. You don't see any vectors.
B.
Right there. And that's what I mean in terms of matching. That's why we look for like a pattern. We said, well, that's what should be going on there. There should be nothing here. No vectors as we can see there. And then they got bigger as you went outward. Makes sense. Hey, the next one we'll look at. Great job so far. That's all we do is just matching. Can we look at this second one? Which I'll enlarge it so we can see that. Can we look at that y, comma y plus 6. This should have an interesting pattern because from my observation, I don't see any x's in here. You agree? Y, comma y plus 6. There are no x variables in there. So I'm thinking, you know, what's going on at 1, 1? and what's going on at 2, 1. Well, the x value, 1 or the x value 2 is not going to affect this, right? Like what would this vector, how would that be?
1/7.
1, 7. But this should do the same, right? Plug in the 1, 7. So at 1, 1 and at 2, 1, we should get vectors that go basically one unit up, but way out like this, but they should be parallel vectors. So we should immediately be able to recognize that vector field. Well, we should see parallel vectors running horizontally, right?
Mm-hmm.
So isn't that interesting? This had no x's, we should see parallel vectors running horizontally. All right, which one's that? Which one's doing that? Pull it down, shrink it. Which one has vector fields running? Oh, I see it. Y'all see a letter D? This one right here. This one's the one, look, they're all parallel vectors there. These are all parallel. Not only parallel, same size and same length. So they're equivalent vectors, right? That's what we're saying. Cool. And who's the last one? So we know that was D. That was vector field D. But what about this last y over? And I chose these 4 on purpose. I thought these all kind of stand out. Y over the square root of x squared plus y squared and x over the square root of x squared plus y squared. Do you notice something? Shouldn't it represent unit vectors?
Mm-hmm.
Because of what we have here in the denominator? So in terms of the vector field, we should find a vector field where they're all unit vectors. You'll notice in this representation here, it's dividing out the magnitude of x squared plus y squared, right? In terms of some y and x. So even at like, what's going on at 1, 1? You have a vector that should be 1 over
Square root.
root 2 and 1 over
Square root.
root 2, but that is a unit vector, right?
Mm-hmm.
So this is different from all the other 3. Every vector should have the same length. Every vector in the entire vector field should be a unit vector. And which one did that? Pull this down, I want to see letter C. I want to hit the light so I can see that. Check it out, this is the only vector field where all the vectors, as you can tell, are the same length. And they're all unit vectors. I mean, plot points like we said before. Cool. Hey, will you flip that page over? We don't have to do all these, but these, right here, this is, you look at me and go, well, those are all the same length. Well, this is called a unit vector field. And all what's going on here is, look at all the formulas at the top, all largest. It's just some software like WinPlot will only make unit vector fields. So, because all these vectors, they get longer and longer and longer, like the last one. Last one is a better representation, but these will get longer and longer and longer, and they'll run into each other. So this is very similar to what they use when they're talking about those hurricanes. They'll just use vectors like this, but they'll color code it to show where they're stronger or longer in length. That would be easy to recognize. And when you see no x's, so shouldn't we see patterns horizontally? I think this will be easy to recognize. What would happen at -1, 1 on that y component?
0.
Yep, it goes 0. That would be easy to recognize. What I want us to, sometimes this can be confusing. Like, how do I know, you're doing it on a test, how do I know which one's y come to x and -x come to y? Because if you plot points like 1, 1 and -1, 1, or 1, -1, I don't know if that gives it away so much. And students get a little worried on a test. So the point I recommend on a y, x versus -xy, I'll write them both down. Yx, what was the other one?
Negative xy.
-xy. I recommend looking at a vector like this. At a point like 0, 2. The only reason I'm choosing it, I picked something, whoops. I picked something right on the y-axis, or some point right on the x-axis. And it should stand out to us. When these almost look something similar, yx, this has x and y, a negative and a positive. So how should this move?
2, 0.
2, 0. So at the point 0, 2, I'll plot it. because on all these vector fields, they kind of look the same. At 0, 2, how should it move?
Go up.
2 to the right,
Right, yeah.
right? In the positive x, and then doesn't go up, does it?
No.
So we should see a vector that does something like that at the point 0, 2, right? And then how about here? What should we see in terms of here's your x-axis and y-axis? All right? At this point, the vector should do what? -0 is just what? Aha! So I picked this point on purpose so I could identify two vectors that are totally different from each other. And then we can go back in here, I'll hit the lights. Which one at this point looks like that, and which one at this point 0, 2 looks like that. We should go find it. So that's what I was saying. I didn't want you to get stressed out like during the test. You go, I plotted 10 points, I still can't tell which one is which. You can find that one point that stands out. So when I'm looking, look at D, look at number 4. I see it. Number 4, I see the vector that's shown up like that. You gotta be this one.
YX.
Yep, the y-axis. Now this one, let me see, where's that? Let me pull that down. It doesn't look like the one in the bottom left corner. I gotta pull this up. There we go. Look at that top left corner. Everyone see that thing? Right? See what's going on right around here? I'm just gonna point with my fingers. But right around, you see these? That's gotta be this one. So that's what I was saying. When it comes to, I can just pick any point? Yeah, but sometimes picking points right on the x or y axis gives it away in the matching vector side. Cool. Okay, great job with that. Couple more things before we move out of vectors. We'll spend most of the time today on 16-2 line integrals is, what about three-dimensional vector fields? Can they be three-dimensional? Absolutely. So and just for that, I gave you a sheet. You'll probably see it with three-dimensional. Nothing crazy, but how about a vector field 1, 2, 3? Guess what you'd notice? Are there any variables in there? Here's a three-dimensional vector field. So if there's no variables, every one of the vectors should be the same size and the same what? Direction? Yeah. They should all move 1, 2, 3. And it could look something like this. And I made this with wind plot. But they're all, notice they're all the same length and the same direction. Same length, same direction. That's just a three-dimensional vector field. I thought I'd give you another one just to look at. What if it did have variables? So let's look at one like that. These have been scaled down because you can see they're almost running into each other. But this is the vector field x, y, 30. So what's going on at the point like 1, 1, 1? It would move what? 1 in the x direction, 1 in the y direction, and 30 upward. But do you notice with this vector field, because the third component, the k component, doesn't have a variable, and it's 30, every one of these vectors should be pointed which way?
Up.
You see that? Because there's no variable in the z component. And that's what you'll notice in this vector field. They do change sizes. These have been scaled though. That's why they look, it's like a unit vector field where it makes them look all the same way. But you'll notice all the vectors are pointed up. That's what's going on with that thing. Cool? Hey, awesome. Well, I will turn this off for now. Take that. Take the light. One more thing. What if I give you a function? Nothing crazy. A function of x and y. That's not a vector field, right? But this is in section 16.1. So when we're in section 16.1, and I give you a function of x and y. I'll read it directly. Okay. Here we are in vector fields. Nothing crazy. How about ys? Whoops. I'm actually screwing up making a vector field. This is a function of x and y. How about just something like, a scalar function? How about x times y? And here's the directions from the book. I want to tell you which problems this is like from the book. This is a problem like, number 21 out of 16.1. They go, sketch the gradient vector field with that. So vector fields, we're talking about vectors, we need a vector field. What's the gradient again? Do you remember the definition? That's the vector that's made up of what in terms of F? See, that's not a vector. Yeah. I'll stand it, Andrew. We're talking about the gradient. I'm going to put del F here. Remember that was the notation for gradient? Or you can put what? GRAD. Gradient, a function is vector. Del F is the gradient. It's just the vector field made up of the partial derivatives. But this is what they're talking about. They want you to sketch this. What is that x? What's the derivative respect, partial derivative respect to x?
Y.
What? What's the partial of that function with respect to x? I mean with respect to y.
X.
X, right? And now you can start plotting the vector. And then you move from there. So if you work those problems in the textbook, I didn't want you to get confused by problems like, this is similar to number 21, where you go, what do they mean this didn't have a vector field? They said sketch the gradient vector field. Yep, they just want you to get the partial derivatives, respect to x and y, and then you start plotting. And you know how to sketch that, right? You know, let's sketch one vector. How about what's going on at the point -1, 1? That's y, x, that's y. How would that move? It would move
-1.
1 in the what? Y direction, and then -1 is not the movement? So I'm going to go plot that. At -1, 1, it should move right 1, and then down 1, which would look like what? Inward. And you just keep plotting away. Alright. Hey, so now we're moving to line integrals. Two types of line integrals we'll be working with today. Line integrals of a scalar function and line integrals of a vector field. Well, here's the formula. Line integral of a scalar function. Can everyone see that? I'll even put it right here on the board. The line integral of a scalar field. Or scalar function. It's written as, first, they put a C here. That C represents actually the curve. So these are called line integrals. Maybe we should call them curve integrals. Most of these problems are going to have curves. All right, and they were a function of x and y, and then they put ds. Okay, what the heck does this mean? First of all, I want to talk about that ds. This ds is represented by this right here, if it's two-dimensional space. If you're talking about a curve in two-dimensional space, that C represents some curve. If it's in two-dimensional space, like a vector curve, you know, that we had before. But this is what ds is. Now, did anybody need me to derive that? I remember you asked me, like, gosh, a couple weeks ago about deriving like the length of a curve. But it's very similar. Do you want me to derive that? I can do it real quickly. Anybody want to see where that comes from? Yeah, everyone okay? Everyone's okay? What do you think? Okay. It only take a couple minutes. We can talk about like where that came from. It actually came from like if you just had a length of a curve. We start out by thinking a distance between 2 points on a curve. So what's the distance one? I'll just derive it real quick. It won't take long. What's the distance? I can think about change in x squared plus the change in y squared. Okay. But do you remember something called the mean value theorem for derivatives? And it said that dy dx equals change in y over change in x at some point c between 2 points. Because the whole idea, if we're trying to get the length of a curve, we've got to break this into what? Just an infinite amount of small segments, like this, and send that limit towards infinity. Okay. Anyways, what does change in y equal to there? We can substitute. What's change in y equal to? dy dx times a change in x. So I'm going to put that in here. Look what you get. You get change in x squared plus, I'm going to put that in there, dy dx, change in x squared. So far, so good? All right, now, what can I factor out of that mess? Here, I'll erase this. Now we put that in there. Can I factor out a square root of x? And it's got to be positive, so I can factor it out of here and just put it in front of the radical. Well, what are you left with? This becomes a 1,
Plus dy.
and you got a dy dx all 1.
Yeah.
Squared. You go, okay, but sum a bunch of these. You're like, aha, infinite sum. We go, all right. I go 1 to n, I'll send a limit towards infinity of all these. 1 plus derivative of y with respect to x squared, and then it had a change in x, right? But this turns into the integral. And you go along the curve from a to b, 1 plus dy dx squared. And what does this become in the integral? Just a dx. Isn't that cool? So this is actually the length of a curve, or when we just came up with how you get the length of a curve. But that's if it's in terms of y's and x's. Everything we're dealing with now is parametric. So how does this get formed? So I'm going to take this one step forward. One step further, we'll talk about that right, okay, everyone? We'll take it one step further, I'll write it right up here. Get this out of the way. We'll be dealing with that in a second. So what do we have there inside that radical? 1 plus a what? dy over dx, and it's all squared. I'm going to enlarge this radical for everyone. And how about we divide a dt here and a dt there? So I'll do it there and I'll do it there. And when I just multiply a 1 to this, can I do that? I can multiply 1 to it. And then, this had a dx outside, so I'll multiply that by dt over dt. And look what happens. If I take this dx dt and multiply it back into the radical. So if I multiply this back into the radical, I gotta think of this as square root of dy dx squared, right? When I put that back in, look what happens. This goes back in here. Dy dx squared. When I put it here, it's gonna cancel with the what?
Dx dt.
I mean, this is I apologize. When I put a dx dt and I put it in here, it would be a dx dt squared. When I multiply here inside, it's going to cancel that out. And then you'll just be left with that. So all I did is when I put this back in the radical and distributed it, look what happened. And we just formed what? What we call this ds. So thanks for being patient on that. I just wanted to see where that comes from. So that ds, you might be in section 16.3 and go, what's ds again? It's the square root of dx over dt plus dy over dt. There's another way we can write that. We can write this as ds just equal to the magnitude of some r prime of t dt. You all agree? Is that another way we can write it? So, the formula's going to what's the line integral of a scalar function? I'll put it back up. It becomes the line integral of a scalar function will be take the function of x and y and multiply that dx. Well, let me do that again. Because we're going to make all this parametric. C is the curve. We'll write the function of x in terms of t, make sure y is in terms of t, everything in terms of the parameter t. So what does this turn into? Well, I'll use this. And we need to write that, but I'll write this one. Just the magnitude of r prime of some t. Okay, so we got our formula, but still, what does this mean? Can we visualize this? So I'm going to go to that. I want you to, can we see that? What are we really finding? It'd be silly if you and I just start working problems like, okay, what does this really mean? I'll make sure that's where we'll use that. Let's see. Use this one right here. Ooh, what does this really mean? This line integral of a scalar function. Oh good, it's coming through. Here's what we mean. You'll see in this picture, everyone, The line integral over the scalar field can be thought as the area under the curve C along a surface Z as a function of x and y. And I'll wait till this fades in a little bit with the colors. I'll show you where this applet starts. This is a pretty cool applet. Like, yeah, we got the wrong. So everyone, here's some surface, some function of x and y. It's the contour map. We're like, okay, can we see it better? And I'll tilt it back down. There's some path, some curve from A to B. But tilt this back down, you can actually see the hills in terms of that contour map. Oh, okay, there's like that, some function of x and y, three-dimensional. But you can think of this line integral of a scalar field can be thought as the area under that curve along some surface. And we know when you do an integral, underneath here would be represented as a negative value. Above here would be represented as a what? It's a positive value. So you can get line integrals that are negative. You can get line integrals that are 0 because of this. But you can always think like, what am I really finding? There's some path C, all right, over some, a surface Z, some function of x and y, and we can think it's the area under the curve C along that surface. Along that surface. That's what we're finding. All right. So we'll come back to that. And then eventually we're going to do a line integral of a vector field. I'll pull this thing right back up and we'll do another image too. But let's work a couple of these. So I'll turn this off. Lets work a couple of these line integrals of scalar field functions. So here's the first one. Let's find, and if you don't want to copy it down, if the problem I'm using is from the 16.1 the 16.2 practice problems. Okay?
Can I ask you a question?
And I want to use, we'll start with number 5.
Can I ask you a question? How do you calculate the magnitude of the r over here with the parameter? Do you do that like x squared plus y squared the same way?
That's exactly it.
Oh,
That's exactly it.
okay.
And that's what you do to get that magnitude of that.
Okay.
And so in this, very good. And that's what I'm saying here is like some r what? Some r represented some
X cosine theta.
x and y.
Uh-huh.
Exactly. And so we're saying what? R, some function x and y, is got some x of t here, and it's got some y of t here. And then we're taking the magnitude of just the
X and y.
derivative of x, derivative of y, and it gets squared. Excellent. All right, Owen, here's what they said. You got to evaluate this. Evaluate. I'm using number 5. C, Y, ds. So the minute you see this, and we have not seen this notation before until this section. We have never seen a single integral written with this little c there off the corner. So that means line integral. That's the notation for line integral. You might think it'd be better to call them curve integrals. Because did you just see a line or a curve in that apple?
Curve, yeah.
It was a curve. So you might go, why don't they just call them curve integrals? Because they're rarely lines, right? But they call them line integrals. So they write this, and what else did they write for this problem? They said they got to give us the curve. Here's C. Here's your curve. They said the curve is, they give you the equation, x is t squared. And what was the y component? Y is 8t. Does everyone see this as parametric?
Uh-huh.
Yeah, the parametric equations. And going from 0 to 3. So we just got to find what? Function composed of RT times this will just be the magnitude of the derivative. Will be that. All right, so I'll put this here. And you'll see that's written like that on this sheet too. Oh, good. Zero to 3, right?
Uh-huh.
And what I need to do, function composed of RT times the magnitude of R prime of t dt, where that's R, right? See how it's written like this? I'm saying this is R of t. It's what? T squared and dt. So can we start here? What does this mean? What does this mean? They wrote a y here. So I'm not gonna leave it y, we're gonna get everything in terms of t. What do I substitute there? You got it. Someone, he says, this is just 8t. No, that's 8t. Why did it? It had a y. So what if this had an x? I would have put the what? T squared. What if this had xy? I would have multiplied. Did you follow me? Oh, we're just looking, whatever they have here, and we're substituting. Very good. Well, what goes next for this line? I have to multiply the, all right, the magnitude, which is the square root of r prime of t, which is, well, what is r prime of t?
2t and 8.
2t, is that derivative? And this term is 8, and I gotta take the square root of
2t squared
2t squared plus
64.
64. And this is what we're doing. This is the line integral of a scalar field. Now we gotta figure out how the heck we can evaluate this. Let me do it again. 0 to 3. Do you want to put the 8 out? I'll do it. See? What's this? Now if you want, you might pull a 4 out of that, but I'm not going to do that. You will notice it's a u sub. Grid eye look. This had a t squared, this had a t to first, so. We did 4t plus 64. What's the derivative? 8t dt. 1/8 du equals a t dt. Bye bye t dt. See you later. And I can put the 1/8 with the 8, and what do you get? We've got the line integral of the square root of u. This would be, we go, what is this again? Well, there's the scalar field, z equals y. We're finding basically the area, right, under that curve along that field there. That's scalar function. What's the square root of u? 2/3 u to the 3/2. I'm going to resubstitute. What would that be? 2/3, because only 8 times a 1/8 became a 1. 2/3 of 4t squared plus 64. And where am I going from?
0, 3.
0 to 3. Although some of you might change the limits. That's okay too. So what's the answer? 2/3 of? What's 3 squared times 4? What's 36 plus 64?
100.
100. Minus, put a 0 in there, what do you get?
64 times 2 over 3.
Yeah. What's 2/3 times 32? 64 over 30? There's your line integral.
Didn't you forget the exponent of 3/2?
Oh, you're the best. Let me do that. Thanks, Brad. You don't forget raised to the 3/2 right there. So I'll put that to the 3/2. So I'm going to do 100 to the what? 100 to the 3/2 minus the 64 to the 3/2. Brad, thanks again. What's the square root of 100 cubed?
10, 10, 10.
10
1000.
times 10 times 10, 1,000. Brad, thanks again. What's the square root of 64? Then you got to cube it. So what's 8 times 8 times 8?
256.
8 times 8 is 64, and then you multiply another 8.
512.
512. So what is 2/3 of
488.
488?
And it calculates.
What's twice 488? I'll put a 3 underneath it. 976?
Yeah.
There you go. I'll put it 976 over 3. And Brad, thanks again, because that 3/2, you remove off it. It's like, whoa! I'm going to wrong answer. I appreciate that. Anyone okay with that? Line integral with scalar field? Hey, the next problem we're going to do, you're going to notice it doesn't have a ds. So you're not going to have to figure out what the heck we're going to do with this. Just set the ds. That's ds. So remember that. Even though wait for an angle. What's the ds again? Right there. You saw us derive it. The square root of dx over dt. It can, oh, by the way, it can have three, it can be three-dimensional. So what else? If this was three-dimensional, this would be the square root of dx dt squared plus dy dt squared plus dc dt squared. Cool. Well, let's look at this problem. That was number 5. Let's look at the one. Look at number 7. I'm gonna put that in the board. it doesn't have a ds in it. It says evaluate. There's that c for line integral, aka curve integral. We got y squared dx plus x plus y dy. Does everyone see the problem I'm referring to? This is number 7, just from the practice problem. And here's curve C. Your curve is given by x equals 2t plus 2. And y equals 3t plus 1. And it wants you to go from 0 to 1. Okay. So I'll erase all this. I'll get this out of the way. I'll leave this up here. But our first observation, everyone, this isn't going to work, is it? That's a what? ds. What is ds? That's ds. This is with respect to what letter? What letter?
D.
That's with respect to x. And you notice with the, I put this even on the notes. This line integral here is with respect to arc length. This line integral right here is with respect to arc length. This would be with respect to x. This would be with respect to y. So what are we going to do with this? You might find this easier. The first thing, most important, we're not going to ignore these. You know what I mean? We're not just going to go put y squared, put x plus y, and do the integral, and put t's. These are important. Something has to get substituted for it. So here's the secret. Can I think of that as x prime of t? So what does dx equal to? See, we're trying to figure out what can I substitute for that dx.
X prime of t multiplied by dt.
There you go. That's what you and I are going to put in place of that dx. Everyone got that? Look, we're going to be like, you go here. Got it? Okay, what's going to go there? Let's put that. What's dy dt?
So y.
Well, that's just the derivative of the y with respect to t, y prime of t. So what does dy equal to? Y prime of t dt. Has everyone got that? That's going there. That's what they mean. Now, if you want to write, I passed out a document with those formulas, but we can put it right here. You know, what does this mean? I'll put another section. And what's the integral of some function of x and y dx? You know what that would be equal to with the line curves? I would say this is equal to, ready? Function of r of t multiplied to, what did I call dx? X prime of t times a dt. You'll see that formula right in your book. And I can now go from an a to a b. Everything is in terms of t's. See, the minute I get everything in terms of t's, you'll notice I wouldn't write a to b. Like some one t value to another t value. So hey, just remember that on a test. That we just don't do what with these. You can tell by my laughter, it happens all the time. So you just go, oh, line integral. I'll just put y squared, I'll just put x plus y, and work the problem, I'll go from 0 to 1. It's like they'll be a little bit off, because this will take on at least a number. Unless you're lucky, they're ones. Sometimes they are ones. You ready to do it? Hey, in a similar manner, what would this be? So imagine, what would this line integral of a function of x and y with respect to y?
So
a line with respect to y, what would be the math formula?
Y prime t.
You nailed it. I'll put a to b. All right, thank you very much. Function of r and t. Function of r and t multiply just y prime of t dt. There you go. Hey, I'm not going to write it, but what if it was a dz? Same thing. Z prime of t dt. Same thing. Okay, so are you all ready to work this problem? Let's do it. One step at a time. What goes there?
3t plus 1 square.
3t plus 1, parentheses squared. Oh, what's the limits?
0 to
0 to
1.
1. What goes here? What goes right next to it?
D,
What is dx? I'm going to write it. It's the derivative of x with respect to t
dt.
right? And what is derivative with respect to t? You go, what about the dt? I'll put the dt way at the end.
So that's 2, right?
What's the derivative with respect to x? Just a 2?
2
So I'll put
dt.
a 2 right there. I'll write it right below it just so you look back and go, where did that 2 come from? You can see, this is the 2. And I'm putting the dt way down here at the end. So that we can do everything in one line. Now, what's here? What's x plus y? Can you just do the math in your head? What's these combined like terms? 2t plus 2 plus 3t plus 1. That becomes 5t plus 3? Alright. Is that okay with that? So I just combine these, x plus y. Now, dy, do I ignore it? No. What does dy mean? Y prime of t. dt. Okay. But let's do it right here. 5t plus 3. And what goes here?
Y prime. So
What's
that's
their
3.
y? 3? And you got it. You just finish off the integral, right? Now you know what to do from here, right? Well, hey, can we just do one more step? We don't have to evaluate the whole thing. How would you get out of that mess? You don't need to use stuff. What would you do? I would FOIL it, right? I'd FOIL that out, expand it. What is that? 9t squared plus 6t plus a 1, and I'd multiply the what? The 2. But from here on out, it's just, what's that? 15t plus 9. Again, you don't have to evaluate the whole integral. I know you know what to do now. Multiply the 2 everywhere, combine like terms, get no use sum needed. Most important to me was you know how to evaluate this if it's with respect to an x or y. Cool. So this leads us to the last formula we'll be doing. This is fun. How about a line integral of a vector field? So this leads to that. Line integral of a vector field. You can see the formula here, everyone. It's f composed of r of t. Well, this is the vector field. Vector field, right? Function composed of that. You'll see this on when I wrote f dot dr. So this is just, let me take this. This is f for vector field f composed of r of t, dart r prime of t. But they just write f dot dr for this. But you'll notice it's going to be a dot product. Because similar to this, I don't know if you can tell. That's why I want to leave this up here for a second. Doesn't this look like the dot product was carried out?
Mm-hmm.
This times the x prime plus this times the y prime. And you bet, that's like a dot product being carried out, which leads us to now what we talked about, a line integral of a vector field. The first thing is I want you to see what it is. So I'll hit this. Power it up. This is pretty cool. What's a line integral of a vector field look like? The last one was a scalar field. What's the line integral of a vector field? So I like this applet. This is pretty cool. Fire that up. Make sure this is the source is names. Then we'll do a couple of these. Last stuff we'll be doing today, but I want to make sure we do at least a few of these. They go fast though. No worries, they go fast. And it's fading in. You're going to see a vector field. The vectors are blue. And they write the formula at the bottom. If you want to read this, the trajectory of a particle in red along a curve inside a vector field. Starting from point A, the particle traces the path C along the vector field. The dot product along that green line of its tangent vector, which is going to be the red arrow, and the field vector, which is the blue vector, all right, is what we're getting out of this. And we're just going to do an infinite sum of that. It's going to be the summation, this infinite sum limit. The limit is you sum these towards infinity of all those dot products. So we'll see this again. Okay, here we go. There's the vector field. Curve C starts at A, goes to B. Now, look at the red vector and the blue vectors. Aren't they going in the same direction at the beginning? So dot products, wouldn't they be positive?
Mm-hmm.
Somewhere around here, you'll notice the blue vectors go against the red vectors. Watch what happens to the integral. Let's get start. All right about here. Do you see what happened? Because those vectors were what? going against, the blue vectors were going against the tangent vector, which was red. And when you do that dot product, that's actually a negative value. And so you're summing, you know, those negative values there. Did everyone see that? I want to see it one more time. Now this was written out. At the beginning, the blue vectors are going in the same direction as that red vector. You'll notice that's given a positive area when we're going to do the integral. Right at the beginning, think of red vector as the tangent to that green path. Red's going in the same direction as blue. And then when does it go against? When does blue start going against it? Right about there. And all these were going against it. Does that make sense? So when think about it, what would be the answer to your line integral of a vector field if half the time the blue vectors went with it and half the time the blue vectors went against it? What would you probably get for your answer?
Zero.
Something like what?
Zero.
What if all the vectors go in the same direction?
Positive.
All the vectors go in the same direction as your red tangent vector.
Positive.
Then you're going to get a positive line integral, right? And what if they all go against it? It's
Negative.
going to be negative. Does that make sense? Because sometimes that'll be asked. I'm not going to do that right now. We'll work some problems, but can we play around with that first? Because it's fast. So I'll minimize this. How about, let's see. I'm going to go to 16.1.16.2 problems, which you have a copy of. Let's go down to number